This is lesson 8 from our No Frills, No Nonsense A-Level Physics lesson series. Lesson 8 is all about the work of leptons. Leptons at work. Now, we have already heard that particles interact and can actually create new particles in that interaction. Previous lessons I've spoken about protons being made to collide with each other and how that turns the energy of the collision into rest energy of particles and antiparticles that are created in equal quantities. And that is actually what we see. In the early days of particle physics, the way it would work is we would have a particle detector here on Earth, and this is on the ground. We'd have lots of air, and then we'd have the atmosphere, like this. And then we'd have cosmic rays coming in. And this still happens, of course, but you have cosmic rays coming in. Cosmic radiation, cosmic rays. And when they strike the atmosphere, they cause a jet of particles and antiparticles, a cascade of particles, which we call a jet of particles. Particle jet. Let's change the color of pen for that. Particle jet, which we can detect with a detector on the ground. So the main part of the early part of particle physics was concerned with, well, how can I improve the detection of these particles, but also how can I make particles myself? And if I can choose the energy that protons collide with, I can choose the maximum rest energy that the created particles and antiparticles can have. And therefore, I can actually do some investigations in the properties of those particles and choose, to a certain extent, what the energy of the particles are as I do that investigation. So in doing these sorts of experiments, it was discovered that there were different types of neutrinos. Different types of neutrinos. We collide leptons together, they create particles and antiparticles. So we collide electrons in positrons together, they annihilate, and as part of that annihilation, you can actually get the creation of quarks and antiquarks, which is absolutely mind-blowingly weird. But you get these showers of particles. Then, in amongst that shower of particles, you've got neutrinos of different types. And the neutrinos that we are interested in A-level physics are the electron neutrino, which we will use the symbol nu subscript e for, the electron neutrino, and the muon neutrino. Now they're so named because they belong to these particle families, the electron family and the muon family. So electron neutrinos, they can interact in a way that can create electrons or even positrons, depending on the interaction. Electron neutrinos, then they're not at all engaged in any interactions with muons. Muon neutrinos are, which is very interesting. And of course, we also have the antiparticles. We have the electron anti, or if you're American, anti-neutrino. And we indicate that by putting a bar over the top. And we have the muon anti-neutrino. Sometimes these are called the anti-electron neutrino and the anti-muon neutrino. And that's okay. You can say that. It's not normal, but no, everyone will know what you mean by it. You're not going to lose marks in exams for saying anti-electron neutrino instead of electron anti-neutrino. It's fine. Now, there are two more categories that I have not included, which is the tau neutrino, or tauon neutrino, which is a third category of neutrinos that were discovered Greek letter tau, sometimes pronounced tor. Tau antineutrino. And we use that Greek letter tau, sometimes called tor, underneath there. Now, they aren't part of our A levels, so we can ignore these to a certain extent. I'm going to say not on A level. Now, there are lots of mysteries to do with these neutrinos. They are an example of what we might call dark matter. If we go back a stage to last lesson, we can see these neutrinos don't interact with the electromagnetic force or the strong nuclear force. They're very weakly interacting indeed. They only interact with the weak nuclear force, but they do have mass, so there is some gravitational interaction as well, although neutrinos are so low mass that we can't detect what that is. But these neutrinos do interact with gravity. They also interact with the weak nuclear force. They are not the type of dark matter that we think is the reason galaxies hold together. There's not enough mass in them for that. But we are interested in how much mass there is, because it's all part of that understanding of the nature of the universe. But these things are even weirder. We're going to teach you things in A-level physics about how neutrinos stay within their lepton families. If electron neutrinos stay in the electron family, and neutrinos that are muon neutrinos stay in the muon family, and so on. But actually that's not true. And we know from looking at neutrinos from the sun that these neutrinos oscillate between families. And we don't know why. And we don't know how. It's one of the many things that's at the cutting edge of modern physics, is trying to understand what's going on. So how do we investigate neutrinos? Well, they're really, really hard to detect because they interact so weakly with matter. We can create them easily enough. All we have to do is have a particle that decays into leptons, such as a pion. We can have a pion or a bunch of pions coming in, and then it will decay, and it can decay into a bunch of maybe muons, anti-muons, and other things. So maybe here we're going to get muons, we're going to get anti-muons, but we're also going to get potentially some neutrinos. Maybe not, maybe we will. If I put something here to absorb and detect the muons, the chances are the neutrinos are going to get through. So those neutrinos are not going to be stopped by that absorber at all. Here they come. We might have our neutrinos, muon neutrinos, and our muon antineutrinos, and they get through whatever our muon absorber is. Absorber might be some sort of calorimeter to measure the energy of those muons. Now what we can do is we can put something of a detector here, some sort of neutrino detector, to try to detect them. And the chances are that almost all of them are going to pass straight through it. They're probably not going to interact. But you might get lucky and have one of them interact like this. So you have a neutrino come in, and then a muon come out. And then, of course, we can detect those muons over here as well with another muon detector or absorber. So we can do clever experiments like this on what we call beam lines detector, beams of pions, or any particles that decay, and investigate these neutrinos and how they interact. And in doing this, what we have discovered is that you only get muon neutrinos when there's muons, and you only get electron neutrinos when there's electrons on this scale. Obviously, that's not actually what happens in reality because of the weird neutrino oscillation for the sun, but that definitely won't be in your A-level because it really is cutting-edge physics. Let's just move that up a little bit, move that out of the way. So maybe I should annotate this to say, talk about the detection of neutrinos. I mean, we use big tanks of water to detect neutrinos. Right, so detection of, how do we spell neutrinos again? Neutrinos. There we go. So we have our neutrinos. We can detect them. We can investigate them. And what do we discover? Well, there are interactions that we do see and interactions that we do not see. We can see, for example, that a neutrino, an electron neutrino, can interact with neutrons in a target and can turn those neutrons into protons, and electrons come out as well. Now, if you look at that, charge is conserved. At the beginning, we have a total charge of nothing. Let's use Q for charge. We have 0 plus 0, and at the end we've got plus 1 and negative 1. So charge is conserved. But there's something interesting happening here. The neutrino changes into an electron. Now, this is the work of the weak nuclear force. So we know there's a W boson involved in this interaction. Which one it is, we don't know. It could be actually either of them, plus or minus. But there is a W boson involved in that interaction. So we do observe this happening. But oddly, we don't observe this happening. So I'm going to put down here that this is observed. But what we don't observe is our neutrino, like this, interacting with a neutron and decaying into an antiproton and a positron. Now, when we look at charge, let's get our charge thing out like this. We've got 0 charge plus 0 charge is equal to -1 plus 1. So charge is balanced. And this would be some sort of W boson. But actually, this is not observed. Is not observed. The charges seem to balance, but we never see this. So what's going on? This is not observed. What's going on? Well, when we look at it closely, we will notice that we have got a particle in the baryon family and a particle in the baryon family where matter is changing into antimatter. But we also have antimatter there. And so we have antimatter and antimatter on the right-hand side, matter and matter on the left-hand side. If we just talk about leptons, which we are right now, then we've got a lepton, which is matter, changing into a lepton, which is antimatter. The positron is antimatter. And that's really why this doesn't work. You can't create antimatter from matter like this. This is antimatter. This is matter. Just like that. So we don't observe that happening. We can look at the same thing with muons. If we look at muons, we get mu minus, like this, which will spontaneously decay into an electron. Muons are just like electrons, but 200 times the mass, but they will decay into electrons. But in doing so, you also get an electron antineutrino, and you get a muon neutrino. How interesting. This is observed. 2 types of neutrinos emitted from this decay of a muon. But what you do not get, if you look at this, you never get this decayed into electron and then an electron antineutrino, and a muon antineutrino. We don't get that. That doesn't happen. Is not observed. There we are, I didn't trip over my words this time. So this is interesting. And again, if we look into this and try and say, well, what is happening here? We have got matter and antimatter, as we had last time. Now, you can have matter and antimatter of the same family on the same side of the equation. That's fine. We create an electron. We create an electron antineutrino. I mean, that happens in beta decay. We're fine with that. But what we don't get is matter changing into antimatter. We never get that. We never get matter changing, spelled changing wrong. Let's try that again. Take off the E, add ing, into antimatter. Spell it with an A. Antimatter. We never ever get that. Let's just move those notes a little bit. Let's move those up a little bit. There we go. We never get that. That is important. That is significant. And we are grouping together the way the neutrinos behave, which is why they're named the way they're named. We're grouping them together. So what is responsible for this interaction? It is a weak interaction, and whether or not we see these decays depends on whether lepton number is conserved. So what is lepton number? Well, it's a new property, a new quantum number, lepton number. It's a property leptons have, and it is conserved, always conserved. So what lepton numbers for what particles? Well, electrons have a lepton number of 1. Positrons have a lepton number of -1. Electron neutrinos have a lepton number of 1. Electron antineutrinos have a lepton number of -1. Okay, so we can see what's going on here. We've got matter and antimatter. Matter has a lepton number that's 1. Antimatter has a lepton number that's -1. Now you'll notice that I've put the subscript E on all of these lepton numbers. And that's because we conserve separately the lepton numbers for muons. We conserve muon lepton numbers, spell numbers right, separately. That might be spelt right. If it's wrong, someone will tell me. Separately. So we now have our muons. They are matter, so they have a lepton number of 1. We've got our antimuons. They are antimatter, so they have a lepton number of -1. We have our muon neutrinos. They are matter, so they have a lepton number of 1. And we have our muon antineutrinos. They are antimatter, so they have a lepton number of -1. Just like that. So this is interesting because it doesn't follow the same thing as charge, of course. We've got that's a charge of -1, that's a charge of +1, that's a charge of 0, that's a charge of 0. We could do the same thing for our muon family of leptons. That's a charge of -1, that's a charge of +1, that's a charge of 0, and that's a charge of 0. We use a Q for charge, we always do. Those are the properties of these leptons, and we conserve charge in every interaction, and we conserve lepton number in every interaction. But the lepton number must be conserved separately for the different families of leptons. So if you want to check whether an interaction is possible, just like we did here, where we laid out our Q's, you would also lay out L's. So lepton number, this is 1 plus 0 is equal to 0 plus, well, this is antimatter, minus 1. Does not work, is not observed. Just like that. And there's no muons in there, so there's no point looking at muon lepton number conservation. And that is how leptons do work. That's what leptons do. It's why leptons, lepton number is conserved. Hopefully you found that helpful.